And hello YouTube, welcome to this video. We're going to talk about Laplace transforms and some of the derivations. Okay, so yeah, I'm going to go through it very quickly. First, I want to talk about some of the LaTeX code I use. Okay, and where I'm going to put it. I'm going to put it into my LabVIEW YouTube playlist or LabVIEW YouTube GitHub repository. And for LaTeX, the document class is ext article, so that I can change font size. So for example, if I want the font size of 10 or 11, I can do that. If I want a font size of 17, I can do that. Note that changing the font size here, the 17 point and everything only works for this ext article. It does not work for the normal article document class. Okay. So Laplace transforms, I assume you know some definitions. We like to use the notation of this curly L, which in LaTeX, you don't have to add any new packages. It's called mathcal. Okay, mathcal. So mathcal and then something, it will just produce this big L. Okay, so that's how I type it out, mathcal. So you can take a look at the code. I'll place it on GitHub. Okay, so the Laplace transform is actually integral of 0 to infinity, f of t e to the minus st dt. So that's the derivation. So the most simple way of thinking about Laplace transform, it's basically it's like a Fourier transform, except it's more extended. Okay, okay. So for Fourier transform, you will have the whole purpose of the Fourier transform is to extract from a periodic signal all the characteristic frequencies. So you can see maybe a frequency 1, frequency 2, frequency 3. So all of these actually correspond to some frequency for some sine or cosine waves, right? So that's what a Fourier transform does. So if you take a look at a Fourier transform, it will be integral of some f of t, e to the minus I omega t dt. I'm not sure what the limits are. I'm not going to elaborate much. Okay. Okay, so the Fourier transform is something like this. If you take a look at Wikipedia, yeah, it will have this. Instead of t, they use x here, but pretty much it's what I like to. I rather use t because it's very intuitive. So you have ix over here and dx. Okay, so omega will be the 2 pi something, 2 pi f. All right, 2 pi f for example. So this is what Fourier transform is like. Now you notice that it looks very similar to Laplace transforms. Yet instead of minus I omega t, you will just have minus st. Why is that so? Okay, so like I said before, Laplace transform is a more extended version of the Fourier transform. So Fourier transform can handle sine or cosine waves, but let's say you have something like this, e to the minus bt and sine omega t. Alright, how does this graph look like? Okay, you will have an exponentially decaying curve like this. These are very common signals to see in engineering. It's an exponentially decaying curve. So how are you going to Fourier transform this? So because if you were just to use the Fourier transforms to decompose the sine and cosine wave, you probably just get this value, this omega value. But this time constant is also very important. Okay, how do you get this out? So the Laplace transform will deal with that. Okay, so remember, actually our Fourier transform is actually something like this, f of t exponential minus I omega t, right? Okay, what is exponential I omega t? This is actually dealing with sine and cosine waves, because imaginary exponentials will relate to sine and cosine waves. So how about exponentials as well? If you want to extract exponential signals, so you will have to add something else here. Okay, instead of just the imaginary part, you have to put a real exponential over here. So the most common way is to use sigma plus I omega t, okay, dt. Alright, so the I omega part will help you to get the sine and cosines out, and this sigma part will help you to extract out all your exponential curves. Okay, so from now you can see S equals to sigma plus I omega, or maybe I would just like to use the letter A. So S equals to A plus I omega. So we like to call this a complex frequency. Okay, complex frequency. Why is it complex? Because it has a real part which deals with exponential curve. This part will deal with the sine and cosine curve. Okay, that's the basics of Laplace transform. So hopefully that gives you an idea of what S is. Okay, this is what S actually stands for in the engineering context, where we like to use S to denote a complex frequency so that we can extract sine and cosine signals. Okay, so again, just want to remind you, for Fourier transform we have this thing called peaks. Okay, we have this thing called peaks. So this will be omega, and we are only dealing with sine and cosine signals. Okay, in Laplace transform we don't just have the sine and cosine signals which will correspond to omega. This will all appear in the imaginary part of the complex frequency. Exponential signals will appear in the real part. So we'll so-called have an A as well. We have an amplitude versus this is a frequency, the imaginary frequency. So if you have a Fourier transform here, you kind of have a Laplace transform. If you Laplace transform a sine and cosine wave, you will also find yourself having a peak in the S-plane. So this is, we like to call it the S-plane. You'll have a peak in the S-plane, except instead of calling it a peak, we like to call this a pole. Okay, why? Because peaks are like, you can use it to describe 3D. Okay, they're peaks and all that. But if you look at the S-plane in 3D format, and you look at the shape of the curve, it doesn't quite look like a peak. It looks like a pole because it goes all the way up to infinity. So that will actually tell you where are all these, what do you call that? Where are all these characteristic frequencies? So if you have a sine and cosine signal, you will have a pole, which is equivalent of a peak in the imaginary part. If you have a exponential signal, you will have a pole in the real part of this S-plane. Okay, so this is a peak showing that, okay, I have an exponential signal. If you have somewhere in between, okay, a pole with in a complex part, somewhere here, for example, so that will tell you that there's a exponential signal with a sine and cosine signal. So this is roughly what Laplace transform will tell you. It can separate out the signal, a time-varying signal, into its various what do you call that, exponential signals and sine and cosine signals. So that's one thing Laplace transform can do for you. Hopefully it gives you some intuition. So now we will just go straight into Laplace transform. Okay, so Laplace transform, as I said earlier, okay, it's like this. So you can check it out on any internet PDF, Google it, whatever you want. Okay, Laplace transform of ft is 0 to infinity ft e to the minus st dt. So in terms of frequency analysis, remember this is complex frequency. S stands for complex frequency. Alright, so the most simple Laplace transform is the Laplace transform of 1. Okay, Laplace transform of 1, let's start. Okay, I have it all written down already, but basically, well, we can do this. I will just comment everything and I'll talk you through the steps. Okay, so yeah, so that you don't have a data overload. Okay, so now let's talk about Laplace transform of 1 and Laplace transform for exponentials. Okay, so Laplace transform of 1 is the easiest. Okay, you have 0 to infinity e to the minus st dt. Okay, then what do you do next? So I'll uncomment this. Okay, so to integrate this, we have the exponential, and then you just divide it by the derivative of the power part here. So the derivative will be minus s, right? It will be minus s. Okay, so you need to evaluate this at t equals to infinity. So at t equals to infinity, e to the minus s infinity will just be equals to 0 for any real value of s. Okay, so yeah. Oopsie. Yeah. There you go. So at any real value of s, when t equals to infinity, this whole thing will just drop to 0. When t equals to 0, e to the minus s times 0 is just 1. So Laplace transform of 1 is just 1 over s. Okay, 1 over s. Okay, what is this telling you intuitively? Well, you can try plotting this out in the plane. You actually have a pole at s equals to 0. Okay, yeah. Okay, so yeah, you have a pole at s equals to 0. Now go and do it yourself and try to think of what this means physically. Okay, so it should be quite obvious once you plot this thing out when you have a pole or peak at s equals to 0. Now when s equals to complex frequency, of course. Okay, yeah. So next part, remember I was saying, Laplace transform it helps you to extract out these exponential signals, right? Not just sine and cosine, but exponentials as well. I mean real exponentials. Yeah, you can do imaginary exponentials for Fourier transform. That's fine, because that's just actually sine and cosine wave. But let's do a real exponential, where this a over here, Laplace transform of e to the at, where a is a real value. There's no complex number here. A real value that's more than 0. Okay, so how do you do this? Okay, so you have e to the minus at times e to the st. What I'll do is, okay, so you just factorize out the t, and you kind of just add the powers together. That's very, very easy. Okay, add the powers together, and then we'll just perform the same integration we did just now. Okay, when we differentiate the power part. Okay, we differentiate the power part. We differentiate the power e to the ast, and then we just put it at the bottom. Okay, so now we will start needing to take some limits, and we have to evaluate this at t equals to infinity and t equals to 0. Now, if you evaluate this thing at t equals to 0, it's very easy. Okay, but the problem is when t equals to infinity, then you have an exponential to the infinity times something, which is a minus s. So that's going to give you some problems, because exponential to infinity is just infinity, It's a crazy big number. I don't know what it is. Maybe it's even undefined. I'm not using all the mathematically right terms here, but it's just in engineering, you don't really think too much about whether something's undefined or infinite. To a physical system, it doesn't really make too much of a difference. Okay, if a signal, so to speak, if let's say a tank you can have, if you have a tank and then you are trying to heat some water in it. Okay, so there's some water flowing in and water flowing out of a tank, and you are supplying some heat to it. If you are trying to take a Laplace transform of this system to determine the inlet and outlet temperatures, if your temperature at the outlet is infinity or undefined, that doesn't make any physical sense at all. So in that sense, undefined and infinity just doesn't make sense, in an engineering context. So yeah, okay, so this is what we will have, right? So like I said, the part where you have t equals to 0 is very easy. This part will just become 1, but you have this infinity here as well. So we'll need to stop and think, okay, what do we do with this? Okay, So I'm going to uncomment this part. So we have this, we just change this part. I'm just going to multiply this minus sign in, then I'll have 1 over s minus a. So we'll have this problem, right? So we'll have this problem. Okay, we are trying to solve this term. Okay, so there's only one. There are a few cases here, right? If a is equals to s, okay, if a is equals to s, you have a 1 divided by 0 problem. So doesn't really matter. Okay. So there are a few cases. A equals to s. So we have a 1 over 0 equals to like infinity or undefined, however you call it. So because you still have this part of the Laplace transform that gives you problems, which is fine. You are basically having a peak at this a equals to s, right? So we have something called a peak, or the proper term is called pole at a equals to s, right? So if you take a look at the denominator, you have on the s plane, if a equals to s, you have this infinity problem, but it's not really a problem. You just call it a pole, all right? Because on the s plane, it does look like a big peak or a big pole. Okay, so if a is more than s, what happens? Okay, then your Laplace transform of e to the at will just be undefined as well. Okay, undefined as well. I just use the infinity term here very loosely, but yeah, it's just, it will not converge or anything. They like to call it not converge. Okay, but what we are more interested with is this 1 over s minus a. And this is what you'll see in most Laplace transform tables and most YouTube videos. There are many YouTube videos doing Laplace transform. They'll use very similar reasoning and methodology. So a minus s less than 0. Okay, a minus s less than 0. Then you have a e to the minus negative infinity. Then this problematic term will disappear. You will just have 1 over s minus a. Okay, so you have Laplace e to the at equals 1 over s minus a. So most Laplace transform tables, they will just assume that, what do you call that? They will just assume that this 1 over s minus a is just there. You'll just have this Laplace transform. Okay, so that's how we deal with this Laplace transforms for e to the at. And you can imagine, right? Imagine for a while e to the minus at, well, you might encounter the problem, but we have to derive it slowly, maybe in the next video. Okay, so what does this show? At least if you just plot this 1 over s minus a, you will have a peak or pole at s equals to a also. Okay, so that what Laplace transform helps you to see is that, okay, we assume we don't have this convergence problem. This 1 over infinity part looks really, doesn't make sense at all. But what it tells you is that as long as you have this 1 over s minus a thing, you're gonna have a very how do you say? You're gonna have a very big issue when t equals to infinity, right? Because as t equals to infinity, your e to the at will just shoot up to infinity, right? So that's what this problem, these infinities here are telling you. Okay, more or less that's what the idea is. Okay, and how do you know what's the use of Laplace transform? Again, it will tell you if you have e to the at, where is this a? Okay, you are going to be able to see everywhere there is this e to the at, you're going to see one of these poles, which will tell you, oh, this is where your characteristic exponential time constant is. Okay, so that's what we have. All right, so I'll leave it, and I'll leave it as it is now, and I'll talk another time, and I'll see you again. Okay, bye bye.